Hello and welcome back. In section 3.1 we work on an introduction to functions. So first we need to learn what a relation is. A relation is a rule that connects two sets. Now, of course, in a math class, more often than not, our sets are going to be number sets. But like in chapter 1, our sets could be really any type of objects. So we have to have two sets, and we have some type of relationship between the two. That's all it takes to be a relation. A function is a relation, ST, common math abbreviation for such that each element of the first set the input corresponds to exactly one element of the second set. So as long as we follow this rule, our relation is also a function. If something is not a relation, there's no need to try to see if it's a function. A function is a special subset of relations. The second set is our set of outputs. Another special name given to the first set, domain, and the second set, range. So our default domain is still the set of integers in chapter 3. Or a subset of integers. Occasionally we do have to restrict the domain, and we've seen some of that happen in chapter 2 problems as well, where we had a restricted domain. All right, so we'll start with an example of a relation involving the temperatures. So C is worth, let's say, 5/9 of F minus 160 all over 9. So the way this one is set up, our domain, the inputs would be F, representing degrees Fahrenheit. Range variable, the output would be C, degrees Celsius. Now we mentioned that we would have to have a rule connecting these things. The rule connecting them is multiply F by 5/9, then subtract 160 over 9. This one also does count as being a function. Every time I enter one temperature in degrees Fahrenheit, it will correspond to exactly one temperature in degrees Celsius. The fact that we have a domain variable and a range variable automatically means it is a relation. So the relation was almost automatic. We had a couple of sets and some type of relationship between them. This is a function. Every single temperature in Fahrenheit has exactly one corresponding Celsius temperature. So one way to write the rule is to just describe it in a sentence. Another way, if we're working with small finite sets, is to do what's called a mapping diagram. In a mapping diagram, we list out the domain, we list out the range, and we use arrows to describe the relationship. So arrows will describe our rule for the relation. So let's try 0, 1, 2, 3, and 8. And a range of, let's say, 0, 1, and 2. So the arrows that I use are going to describe my rule. So 0, I'm going to map that to a 1. 1, I will map that to the 0. 2, that's going to get mapped to the 1. 3, that will get mapped to our 0. And 8 will get mapped to the 2. So these arrows are one way. We start in the domain, we end up in the range. So the fact that we have some type of rule connecting these two sets means we do definitely have a relation. Does this qualify to be called a function? So skim that definition one more time and see if you think it qualifies to be called a function. Okay, welcome back. If you paused it to kind of check over your notes and make your decision, this one is a function. If I tell you that I'm handing you an input, a domain value of 8, you could tell me for sure, okay, the output value that I'll give you back is a 2. If I told you that my input value was a 2, you would tell me for sure, written in stone, okay, your range value was a 1. No questions. Nobody in the domain went to 2 different places or more. Everybody went to exactly 1 place in the range. So our rule in this case is still going to be the arrows. Let's try 0, 1, and 2. And we'll try range values of U, V, P, and B. So 0, I'm going to map to U and to V. So the arrows, remember, are the rule. 1, I will map to range element P. 2, I'll map to range element B. I have a domain and a range and something connecting them. This is a relation. Is this a function? Pause it if you need to. Welcome back. So if I gave you a domain value of 2, you would tell me, okay, I know what range value to give you back. I'll give you a range value of B. I could do that also with the 1. If I tell you I'm going to hand you a domain value of 1, you would give me back a P. But here's where we run into trouble on this one. If I hand you a domain value of 0, now you don't know what range value to give me. Do you give me the U? Do you give me the V? We don't know. So this is what disqualifies this from being a function. So 0 corresponds to both U and V. So that's one domain value, 2 or more range values connected with it, not a function. So as you saw, it can be numbers, but it doesn't necessarily have to be numbers. Now, more often, our rule is going to be a set of mathematical instructions, though. Since being a math class, we're obviously going to be more interested in the numerical values. But we'll do another diagram. This one not a mapping diagram, though. So domain, we'll go on 0, 1, 2, and 3 in our domain values. Our rule this time will be multiply each domain value by 7, then subtract 20. That will give us our corresponding range values. So domain value of 0, I'll do 0 times 7, then add, subtract 20, my apologies, subtract 20, so 0 minus 20, we have a range value of negative 20. Domain value of 1, 1 times 7 minus 20 turns into 7 minus 20, a range value of negative 13. 2 times 7 minus 20 turns into 14 minus 20, a negative 6. And finally, 3 times 7 minus 20, 21 minus 20, and that will give us a positive 1. Now, more often in math, our instructions for the rule aren't given by these sets of instructions using words. Typically, they're done in symbols. So more often, how you would see this problem set up would be domain, and we'll pick a letter to represent it. Usually we'll use X for the domain. Sometimes T for time is another common domain variable. X is sort of a common one. So our rule would also be written in symbols instead of this long drawn out description we have here. So multiply the domain value by 7, then subtract 20. And our range value, typically we would call that then a y, so we'll say that will be our y. That will equal our range value. The rest would look pretty similar to what we already did. So then y is equal to 7 times 0 minus 20, which is 0 minus 20, so y equals a negative 20, and so on. you can complete that table on your own. Now, as far as range variables go, y is a common one, but we also can use function notation. Function notation, we're naming the range variable. But within it, we also give a little acknowledgement of what our domain variable is. So f of x is a common range variable. So f would be the name of the function. And x is our domain variable. So then taken together, f of x then is the range variable. A little bit more vocab as well. We've been talking about inputs and outputs. We also will sometimes refer to these as dependent and independent variables. So just a little bit of vocab. Sometimes called the input, sometimes called the independent variable. Called the independent variable because you get to pick what input you're going to plug in. What you get out of it depends on what the rule says you'll get out of it then. So the range variable, we've referred to it as the output as well. Also the dependent variable. So a little vocab to get out of the way. All right, so let's work through just a couple quick examples that use this. So another common function name would be g. So we'll say g of x is x minus 7 quantity squared, and that we are given a domain of, we'll just have a restricted domain, 0, -4, and +9. So our pieces of the puzzle here, our domain variable is x, our range variable is g of x, our rule is basically given. G of x is the same as x minus 7 quantity squared. So take your input, subtract 7, then square the result. So to find our range values, we'll just set up our little table. So our domain, we have 0, we have -4, we have +9. Our rule, g of x, is worth x minus 7 quantity squared, which will give us our range values. So g of 0, so this is another part of the notation. So notice this is no longer g of x, this is g of 0, the thing that I am plugging in. So g of 0, so this is saying, okay, follow the framework of the function that we named g, all of your x's are now zeros. Keep all the other stuff the same. Then we simplify. So then g of 0, negative 7 quantity squared, which is positive 49. So that is our corresponding range value. Leave myself quite enough room there. My apologies. So g of negative 4, we'll slide the 9 down for later. Again, same idea. This is the name of the function, so it tells me follow this framework, something minus 7 quantity squared, except your something now is a negative 4. So g of negative 4 is negative 11 quantity squared, which is 121. So that is our range value corresponding to a domain value of negative 4. We'll try it out with the 9 as well. G of 9, something minus 7 quantity squared. This time our something is a 9. So g of 9 is worth 2 squared, which is 4. So I have an output value of 4. So our range for this problem, we would have 49, 121, and 4. All right, another common name for functions, h. So we'll do, oh, what the heck, we'll do h of t since we do work with time periodically. H of t is going to be t squared minus 5. I'm going to ask you to identify the domain variable. Range variable. Rule. And find the range values. Given domain of, oh, I pick on here, negative 5, 0, 5, 10, and 15. So go ahead and pause it, see if you can find all of that information. Okay, welcome back. So domain variable, here is t. Range variable would be h of t. Our rule relating them, h of t is worth t squared minus 5. And we'll just make our table. So our domain, our t values, we had a negative 5. And I'll just do them one at a time. Our rule, h of t, t squared minus 5. And our corresponding range value when we're done. So h of negative 5 is negative 5 quantity squared. Yes, you need those parentheses there. So h of negative 5, positive 25 minus 5, for an output of 20. Input of 0, h of 0. 0 quantity squared minus 5, so h of 0 is 0 minus 5, which is a negative 5. And we just continue in that manner. H of 5, 5 squared minus 5, so h of 5 is 25 minus 5, which is a 20 for a range value. So we did have a repeated range value. That's okay, that happens sometimes. 10, h of 10. 10 quantity squared minus 5, so h of 10 is 100 minus 5, which is 95. And finally the 15, h of 15. 15 quantity squared minus 5, so h of 15, 225 minus 5, which is 220. So our range values, 20, -5, 95, and 220. You might be asking, well, what about that other 20? Remember, when we're listing the elements of a set, we don't list any elements twice. So if I listed out that 20 is part of the range, 20 is part of the range, no matter how many other times it crops up. I don't have to list them all. One time is sufficient. So then we kind of wrap up the section playing with some of our other special functions. So we've seen some quadratics, some linears. Next up, we'll take a look at the rational guy. So let's say we have P of Q is 24 over Q plus 2. And then we have a domain given of -4, -3, -2, 1, and 2. On this one, we actually would have to put up a restricted domain. So notice one of these guys would give us a 0 in the denominator. So we would have to create a restricted domain. Our restricted domain, we can use -4, -3, 1, and 2. I can't use that -2 though. So I'm going to ask you to pause it and see if you can find the range values. Welcome back. So we have our domain, our rule. P of Q is 24 divided by the quantity Q plus 2. And that will spit out a range value. So we'll start with our friend, the -4 in our restricted domain. So P of -4 is the left-hand side. Yes, you do need both sides of an equation. So 24 over -4 plus 2 is 24 divided by -2, which is a -12. So a range of -12. So our domain variable is Q. Our range variable is P of Q. And then we just plug in the rest of the restricted ones one at a time. P -3, 24 divided by -3 plus 2, which is 24 divided by -1, which is -24. And that is our range value. Trying out, now we'll skip ahead to the 1 since we can't use the -2. P of 1, 24 divided by 1 plus 2. So that's 24 thirds, which is +8. And our last range value comes from plugging in a 2 for our domain. So P of 2, 24 divided by 2 plus 2. So 24 fourths is a nice pretty 6. So our range, we have a -12, a -24, an 8, and a 6. All right, so that was our friend, the rational. Next up, we get to play with a radical, and I also want to introduce another way to list out answers. The ordered pair can also be used to describe the relationship. So ordered pairs can describe either relations or functions. We're going to use it on a function. So our domain values are going to be x's for this next example. Our rule is going to be f of x is the square root of the quantity x minus 5. we'll get out of that a range value, and then one more thing, we can make ordered pairs. All right, so on this one, clearly I can't use a domain value like 4. If that were listed in the original domain, I would have to go to a restricted domain. X equals 4, I would have the square root of a negative number. Square root of a negative kicks us entirely out of the real numbers. So I can start with a 5 though. So f of 5, square root of 5 minus 5, which is the square root of 0, which is 0, range value of 0. So our ordered pair, I plugged in a 5, and out of that I got a 0. So then we'll take a look at some other numbers. We want nice, neat, pretty perfect squares under here. So the next perfect square we can get, put a little note there. After 0, the next perfect square is 1. If I plug in a 6 for the x, I could get a 1 underneath. Square root of 1 is 1, so a range value of 1. So 6, 1 would also be an ordered pair on here. 2 is not a nice, neat, pretty perfect square. 3 isn't, but 4 is. So think of what x I would have to plug in here to get a 4 underneath the square root. Hopefully you figured out that 9 would be our candidate. So f of 9, square root of 9 minus 5 is square root of 4, which is the nice, neat, pretty integer 2. So there's our range value. So 9, 2 is a nice ordered pair we have here as well. So let's see, we got a 4 underneath. 5, 6, 7, and 8 are not perfect squares, but 9 itself is. Think of what you would have to plug in for x to get a 9 underneath there. So hopefully you came up with our friend the 14. So f of 14, square root of 14 minus 5, both of which are under our radical. So that is the square root of 9, which is 3. So a range value of 3. So 14, 3 would be another ordered pair associated with this function. Okay, so next up, we have you all try one out. So you're going to complete the chart for domain values are going to be x's. Our rule is going to be g of x is absolute value of x minus 4, close it up, plus 2. You'll find a range value from that and try an ordered pair. So our x values, let's see. So let's try 2, a 3, a 4, a 5, and a 6 should be sufficient to find a pattern there. So go ahead and pause it, see if you can complete that chart. Okay, so g of 2, absolute value of 2 minus 4, close it up, plus 2 outside. Absolute value of negative 2 plus 2. Absolute value of negative 2 is 2. 2 plus 2 is 4. So 2, 4 is an ordered pair on this function. Similarly, g of 3, absolute value of 3 minus 4, close it up, plus 2 outside. So that's the absolute of negative 1 plus 2. Absolute value of negative 1, though, is positive 1. 1 plus 2 is 3. So 3, 3 is an ordered pair on this thing. G of 4, absolute value of 4 minus 4, close it up, plus 2. So that's the absolute value of 0 plus 2. Absolute value of 0 is 0. 0 plus 2 is 2. So 4, 2 should appear on this function. G of 5, you should have come across a number that we've seen elsewhere in the problem. So absolute value of 1 plus 2. Absolute value of 1 is still 1. 1 plus 2 is 3, and we've seen that output of 3 before. Now it's associated also with an input of 5. G of 6, also a familiar output. So absolute value of 2 plus 2. Absolute value of 2 is still 2. 2 and 2 is 4. So 6, 4 should be in our collection as well. All right, so that should give you enough to work with the 3.1 exercises. Remember, those are at the end of the chapter, not the end of the section. If you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.